And so a key to understanding this evolution, and particularly the coevolution of Earth and life, is an emerging field called mineral evolution. This idea was introduced in 2008 in a paper that appeared in American Mineralogist. And I think of this as the very early part one of a three-part story about the evolution of mineral evolution. The earliest part was very qualitative. It was a story of the increasing diversity and the changing distribution of minerals at Earth's surface. And so you look at Earth and you see new chemical processes, new physical processes, and ultimately new biological processes that created new kinds of minerals. Now, I'm going to use the term mineral species tonight. And for some people, especially people in the biological sciences, that's a very odd concept, a species of mineral, but it has a very formal definition by the International Mineralogical Association. Every mineral has to be a naturally occurring solid. It has an idealized chemical composition like SiO2 for quartz. It also has an idealized crystal structure like the quartz structure. And every combination of chemistry and structure that's unique is a mineral species. There are about 6,000, I think as of this morning was 6,034 approved species, and about 100 new ones every year. So this is still a very dynamic, active field. So mineral evolution looks at several aspects of minerals: the changing diversity, that increasing diversity, the relative abundances of those minerals, the compositions. That includes trace elements, minor elements, the isotopic composition. They tell us stories, and also the size and shape. And, you know, when you go to the museum, this incredible museum here just across the way, you see these beautiful crystal forms and the shapes and the colors. That's not part of the formal definition of a mineral species, and yet they're so important for us to understand the stories the minerals have to tell. So we're interested in all these. We think about the near surface, the upper 3 kilometers of the surface. That's where you can go down in mines, where you can see them and study them on Earth. It's also what we're most likely to find on other planets and moons, and it's where biology interacts directly with the rocks. And we'll see that biology is really important. So I have to make a comment about the word evolution. Right from the start, 2008, we got pushback on this because the word evolution has several meanings. Now, the most basic general meaning of evolution is just change over time. And we know that happens. We see it around us. We see it in our own lives. Norman Bowen in 1928 talked about the evolution of the igneous rocks. And we talked about the evolution of stars and the evolution of planets and the evolution of meteorites and all sorts of things. It also, in our usage, implies increasing complexification or diversity or patterning. So an evolving system becomes, in a sense, more interesting through time. And there's a congruency, that is, each stage of mineral evolution or any other evolving system follows logically and builds on what came before. So it's a sequence, but it's not this. So erase it from your minds. Don't think about that. It's not Darwinian evolution. And as we'll see later on when I start talking about the missing law, there's something very special about minerals as an example of a much more general natural phenomenon of evolution. So here's the soundbite. If you need an elevator speech, new minerals form through a combination of chemical, physical, ultimately biological processes. And we can trace those changes through planetary history in 10 stages. So the 10 stages is a narrative starting very long time ago, more than 4.5 billion years, and going up, up, up in these stages that are somewhat overlapping and tell the story of Earth's evolution. The earliest stage is actually what we call stage 0, or the minerals, after meaning the original, the primary, the founding. And these are minerals that formed around stars long before our solar system. Stardust, if you will. These minerals form when an old star starts expanding its atmosphere, gets cooler, and it's also rich in some of those mineral forming elements. So we see about 20 different minerals. We see about 12 different essential elements. When you combine those, you have the question of mineral evolution. How do you go from these stardust minerals, 20 minerals with 12 different elements? So what we see today, over 6,000 minerals with 72 different essential elements. That's the story of mineral evolution. And as I say, it takes place in 10 stages, the earliest ones being the condensates around that solar nebula. You can imagine something in space, a shock wave from an exploding star may have caused the initial perturbation, and a cloud of dust and gas began assembling, collapsing in, rotating. 99% of that material went to form the sun, which ignites, which sends out pulses of heat and melts the surrounding bits of dust into little droplets. They cool, they form igneous minerals. That's stage one, 90 minerals or so. Those droplets condense into larger and larger bodies. And you can imagine this big and this big. First, it's electrostatics, but then gravity takes over. 10 kilometers, 50 kilometers, 100 kilometers. And when you get that large, the body starts melting internally from internal heat. And you separate out the metal to make a metal and iron nickel core. You have a silicate magma. You start making new minerals. You have aqueous alteration. You have thermal alteration. You have impacts that create new minerals. About 300 minerals in all. That's what we find in meteorites. That's what we think is probably, when you start forming planets, the end point for a dry world, like the moon, like Mercury. About 300 minerals, but it's difficult to imagine you get very much more. If you have a wet world, like early Earth, like early Mars, you can start doing new tricks. You can make clay minerals. You can make hydroxides. You can make ices at the cold poles. And so this gets us up to an estimated 450 minerals. That's stage 3. We think that may be the end point of Mars. Stage 4 is the formation of all those beautiful pegmatite minerals and granites. Granites form on Earth because you have a hot, big planet that's coated by basalt. And when you heat basalt from beneath, and it's wet, it melts, it partially melts. And that first melt is actually much richer in some elements like silicon and aluminum. And so you form this granitic melt. It comes up to the surface, it forms continents, and those continents are mineral rich, about 1,000 in all. So Earth has this trick. We don't know of any other planet in our solar system that could make pegmatites. But we do even more on Earth. We have plate tectonics. And that means you're recycling fluid rock interactions of the not only the crust, but also the upper mantle. Many, many millions of cubic kilometers of rock that's reworked. The fluids circulate, they concentrate elements. New kinds of magmas come up. New kinds of volcanoes form. You have ore deposits, these massive base metal deposits with sulfides, hundreds of salt-basalt minerals that never would have occurred before this point. You also have tectonic mountain building, which also creates high pressure, stressful environments where new minerals form. And also plate tectonics brings some of those high pressure minerals to the surface. So for the first time, you have all sorts of interesting high pressure minerals that never before graced the surface of our planet. And that's stage 5. And those first 5 stages give us about 3,000, maybe 3,500 or so minerals, purely physical and chemical processes. And that's it. We can't come up with any other mechanism that makes minerals. So how do you get to 6,000? And I've given you the punchline already if you've been paying attention. It's life. Life is an incredibly important component in the evolution of minerals. And that's kind of ironic because life could not have emerged without all the amazing things that minerals can do. They can catalyze reactions. They can actually serve as reactants, part of the chemicals that make life, templates, protection, scaffolds, all these different things. So here we have the situation where minerals play a critical role in the origin of life. Life emerges, and then life plays a critical role in the origin of minerals. And this is the co-evolution of minerals and life that has taken place over 4 billion years of Earth history. Now, stage 6 makes these beautiful stromatolitic forms, makes banded iron formations, makes other kinds of things where microbes do a lot of the mineralization here. But we're not making a lot of new minerals. What the microbes do is they just speed up the formation of minerals that probably formed anyway. The game changer is when life learned how to use sunlight to break water apart and to release oxygen. That's photosynthesis, and that rise of oxygen in the atmosphere essentially rusted the planets, but not just iron. All different kinds of elements are sensitive to that presence of oxygen. And so, for example, copper minerals. at least 2/3, maybe more, of all the copper minerals known on Earth could not have formed before you had oxygen in the atmosphere. They're near surface secondary minerals, which are so beautiful in the collections of copper minerals, for example, at the museum across the way. But it's true also for all these other elements. They're called redox sensitive. They're sensitive to the presence of oxygen, and new minerals form at the surface by the thousands. So that's much of the Earth's mineral diversity. Stage 8 is a period of about 1 billion years in which the oceans, they were oxidized at the surface, where they were in direct contact with the atmosphere, but it took about 1 billion years for the oxygen to penetrate all the way to the bottom as it is today. And once you do that, then you get rid of all the ferrous iron, the reduced iron in the ocean. It forms those iron formations at the bottom of the ocean, and then you can start doing new things. It also caused great swings in the climate because suddenly the atmosphere changed, the climate changed. You had periods, cycles, where Earth became very cold, and by some models, it was covered with snow and ice from the poles all the way to the equator. And that means that the most abundant mineral on Earth by far was ice. Ice, yeah, ice. It's the H2O. That's the idealized formula in the ice crystal structure. So that's one of the 6,034 minerals. But then there are other times the climate got incredibly hot. It swung dramatically from icebox to hothouse, and ice may have gone completely extinct on Earth for some periods of time. And then when it gets cooler, ice comes back. So minerals can go extinct. They just don't necessarily go extinct forever. And then stage 10, this is when life learned to exploit minerals. When life came onto land, you had new soil forming processes with root systems. You also had all these different kinds of fascinating mineralization of shells and teeth and bones, minerals associated with the decay of organisms, minerals associated with coal measures. This is biomineralization. And I have to tell you a story. It's a secret. I know I said I love minerals, but I basically collect trilobites. Okay, so I've been collecting trilobites for a long time, and trilobite eyes have always fascinated me. This is the first trilobite that I ever collected. I was like 9 years old. It was from Silica, Ohio, and it just hooked me. The little eyes are, right now, they're made out of pyrite. The shell is cut. But the original trilobite eyes, those little lenses I'm looking at you, originally were made of calcite, CaCO3. And they were single crystals of calcite with the C-axis pointing out at you. So if you can imagine, every one of those eyes was a calcite crystal with a C-axis. But there's a problem, because calcite makes a terrible lens. Red light and blue light bend differently. So everything is out of focus. What to do? Evolution always finds a way. It selects for the function. And in this case, if you just substitute radially different amounts of magnesium for calcium, you can correct for this chromatic aberration. And that's what the trilobite eyes do. They're incredible examples of nanoengineering. Every eye is radially zoned in calcium, magnesium to correct the bending of light so that they make a perfect eye. That's evolution. It always finds a way.